Section 6.1, Antidifferentiation. Now, up to this point, we have talked about the derivative, we have found derivatives, we have used derivatives to help us answer questions. Now, we're going to play a different game. We're going to say, given f of x, what function would you get as an answer when you took its derivative? So, specifically, the question that we're asking is if you could do differentiation in reverse, what would you get? Suppose that this function f of x, lowercase f of x, is a given function, and capital F of x is a function having lowercase f of x as its derivative. That is, capital F prime of x is equal to lowercase f of x. We're going to call capital F of x an antiderivative of f of x, lowercase f of x. And so let's think about this for a moment. Let's suppose for one moment I said, what function's derivative is 3x squared? Hopefully you would tell me that if you took x cubed and you took its derivative, you would specifically get 3x squared. Okay, great. Thus, an antiderivative of 3x squared is x cubed. Now, trick though is that that's not the only one. Well, let me name another one. How about x cubed plus 1? Because if I took the derivative of x cubed plus 1, the derivative of x cubed would be 3x squared, and the derivative of 1 would be 0. And know another one? How about x cubed plus 5,000? Same thing happens. Take the derivative of x cubed, you'd get 3x squared, and then the derivative of 5,000 would be 0. And so, the derivative of all three of these functions is x cubed. In general, I could write the antiderivatives of 3x squared as x cubed plus any constant. Because, of course, the derivative of a constant is always going to give us 0, and so when we take an antiderivative, you have to take into account that the derivative would have gotten rid of all those constants, and so you have to write them back in, but the way we're going to write them back in is just with plus c. Now, we would like a nice way to write this. So, let's say that lowercase f of x is a function. And suppose you have found an antiderivative, capital F of x. Then all antiderivatives are of the form capital F of x plus c. And the standard way to express this is to write this symbol, f of x dx, is equal to capital F of x plus that constant c. Now, let's talk about notation. So technically this symbol is called an integral sign. And so the entire notation, the integral of f of x dx is equal to capital F of x plus c, is called an indefinite integral. And it stands specifically for the antidifferentiation of the function f of x. So, let's actually do some of these. Let's think about this. So, from the above, the integral of 3x squared dx is specifically x cubed plus c. Alright, we found that to be true. And so let's try a slightly different one. Let's find all antiderivatives x cubed. Okay, so let's think about this. We want to write, first off, the integral. That's the antiderivative of x cubed. We do need to have that dx. That tells us, if nothing else, what we're taking the integral with respect to. And so I'd like to figure out what things could I differentiate to get x cubed. Alright, well let's think practically for a moment. So let's do a little sidebar. Let's take the derivative. Hopefully you're going, okay, x cubed, we know that the standard power rule makes you have one less power. So I need to take the derivative of x to the fourth, right? Some form or fashion. I'm leaving some space because I'm going to write some more stuff. But the derivative of x to the fourth is going to be 4 times x cubed, right? Okay, so let's think about this. What could I multiply times both of these sides to get me x cubed to go into it? Well, if 4 is here and I need to get rid of it, why don't I divide by 4? So I could divide by 4. Well, then what happens? I've then got the derivative of x to the fourth over 4. That gives me 4x cubed over 4, which leaves me with x cubed. Okay, that's our winner, right? So the derivative that I'm going to take of x to the fourth over 4, if I take that derivative, I'm going to get x cubed. Well, that tells me specifically that my antiderivative is then going to be this thing that we would have taken the derivative of to get x cubed. Well, that's going to be 1/4 x to the 4th, but because we want all antiderivatives, I have to take into account that there could be any number of constants c there to give me zeros. Alright, so hopefully you're kind of recognizing the pattern, but regardless, let's write down some formulas to keep us on track. How, in general, can we take antiderivatives? Well, I claim that we have a power rule for antiderivatives, or integrals, just like we had a power rule for derivatives. So specifically, if we have x raised to the r power dx, taking the antiderivative of that, that's going to be 1 over r plus 1 times x to the r plus 1, all plus some constant c. Now we do have a limitation here, that is r can never be -1. If r is -1, well, that doesn't quite work, and we're actually going to have to deal with that natural log stuff. Now let's consider the antiderivative of the exponential. Well, if I have e to the kx dx, well, the antiderivative of that, or the integral, is going to be 1 over k times e to the kx plus some constant c, where of course k cannot be 0. Then if I have the integral of 1 over x dx, well, what's that going to give me? Well, recall that the derivative of the natural log function gives us 1 over x, and so that's going to be the natural log of, we have to be a little bit careful here, the absolute value of x plus some constant c, where of course we do have the restriction that x can never be 0, and the absolute value takes care of the negatives. Some other things that you get are that the integral of sums is the sum of the integrals. And so if you have sums, you can break it up, and you can do them separately. And we also have that if you take the integral of a constant times a function, that's the same thing as the constant times the integral of the function. And so luckily we get a few nice properties to help us out taking antiderivatives. Okay, so now let's take some more antiderivatives using these properties. We want to find the antiderivatives of 9x to the 8th. Okay, let's write that. That is the integral of 9x to the 8th dx. Well, the integral of a constant times a function is a constant times the integral of the function. Then we can just use our general power rule, and so that's going to be 9 times, well, 1 over 8 plus 1, 1 over 8 plus 1, times x to the 8 plus 1, all plus some constant c. And so then we can clean this up a little bit. I could really distribute that 9 to the c if you want, but recognize that a constant times a constant still is a constant, so it doesn't really matter. And then 9 divided by 9 is 1, and so I'm left with x to the 9th plus c. And so this is all of the antiderivatives of 9x to the 8th. Well, then let's determine the integral of x cubed dx. Well, we have a constant times a function, so that's going to be 1/3 times the integral of x dx. And so then we can use the general power rule because r is not -1, and so that's going to give us 1/3 times x to the 2nd divided by 1 plus 1, or 2, of course plus some constant c. And so this simplified is x squared over 6 plus any constant c. And so those are all of our antiderivatives. Alright, let's find this antiderivative. Well, first off, notice that this is the integral of sums, so that's going to be the integral of 4 over x dx plus the integral of 6 over e to the 2x dx. At this point, I'm going to try to pull the constants out front and get them all in nice forms. And so for that first one, I can pull the 4 out, so that's really 4 times the integral of 1 over x dx. Plus, I can pull the 6 out front, so that's 6 times the integral of 1 over e to the 2x. But if it's e to the 2x in the denominator, that's the same thing as e to the negative 2x dx. So now it's in the numerator instead of the denominator, which is really what we need, because then we can use our formulas. So this is then going to be 4 times the integral of 1 over x. Well, that's going to be the natural log of the absolute value of x. And I know technically you have to deal with a constant that occurs for that integral, but I'm just going to put them all in the end, because if you add a bunch of constants together, you're only going to get one constant. And so this is 4 times the natural log of x plus 6 times the antiderivative of e to the negative 2x. Well, that's going to be e to the negative 2x divided by k, where k is negative 2. And so then I'm going to throw in that constant in the very end. I am going to clean this up a little bit. This is then 4 times the natural log of the absolute value of x plus 6 times negative 2 is negative 3 e to the negative 2x. Don't forget plus that constant c. So this is the indefinite integral, or all of the antiderivatives. Now, one thing you can always do, if you want to confirm that your evaluation is correct, just take the derivative of what you just found. When you take the derivative, you should get what you started with inside the integral. All right, integral of sums is sum of the integrals, so that's going to be, and I'm going to go ahead and do some rewriting as I go, the integral of x raised to the 1/2 power dx plus the integral, and I'm going to rewrite this to make our general power rule easier, x to the negative 3rd dx. Well, this is then going to be x raised to the 1/2 plus 1, but 1/2 plus 1 is 3/2, divided by 3/2, plus the integral of x to the negative 3rd is x to the negative 3 plus 1, or negative 2, divided by negative 2, all plus some constant c. Then, of course, if you want to clean this up just a little bit, you could. Fraction division is multiplied by the reciprocal, so that's times 2/3, and so that's 2/3 x to the 3/2 minus x to the negative 2nd over 2 plus some constant c. And so there's our integral, or all of our antiderivatives. Alright, so now we want to find the integral of 2 plus x squared times 4 minus x dx. So, we don't want to work ourselves too hard, and the truth is there's not a super neat product rule that we're going to learn about right now that will help make this integral easier. So what we need to do is we need to simplify the stuff inside the integral. And so this is going to be the integral of, and then we need to do the binomial multiplication. That's going to be 8 minus 2x plus 4x squared minus x cubed dx. And at this point, if we can combine like terms, we probably would want to, but after that, we're just going to break it up over sum. Well, then this is the integral of sums, and so we can break it up, and any constants that we can see we can pull out front as well if you so desire. So this is the same thing as the integral of 8 dx minus 2 integral of x dx plus 4 integral of x squared dx minus the integral of x cubed dx. Well, this first one, the integral of a constant, well, think about what happens, right? The constant times x, if you take the derivative of a constant times x, you're going to get just the constant. And so the antiderivative of a constant is going to be that constant times x. And so we're going to get 8x minus 2, and that's going to be x squared over 2, plus 4 times x cubed over 3, minus x to the 4th over 4, plus some constant c. And if you wanted to simplify it some, we could. This is just 8x minus x squared plus 4x cubed over 3 minus x to the fourth over 4 plus some constant c. And so there's our antiderivatives, because c could be anything. Okay, so let's look at what we've got going on. They're telling us that f prime of x is equal to 8 times x to the 1/3. And then specifically that f of 1 is equal to 4. Now this is actually called an initial value problem, because they're giving us a value, and if they give us a value, then we should be able to find the exact constant. Alright, so that's our hope. So we won't be looking for all the integrals. We'll be looking for a very specific integral where the constant ends up giving us f of 1 is equal to 4. Alright, so let's write all this out. So specifically, we don't know what the function f of x is. We don't know. But we do know that if we take the integral of f prime of x, that's going to give us f of x. So the integral of 8x to the 1/3 dx will give us the correct antiderivative, which will give us at least the form of f of x. That's then going to be 8 times x to the 1/3 plus 1, that's 4/3, divided by 1/3 plus 1, that's 4/3, plus some constant c. At this point, I think I'm going to simplify it just a little bit. Fraction multiplication from the fraction division, that's going to be 8 times x to the 4/3 times 3/4. 8 divided by 4 is 2, and so this is really going to give me 6, 2 times 3, 6x to the 4/3 plus some constant c. I should have left that c there. So plus that constant c. Okay, that's all right. But what do we know? Now we found our f of x, sort of. But we're also told that if we take f of 1, we're going to get 4. And so let's take f of 1. Well, that's going to be 6 times 1 to the 4/3 plus that constant c is equal to 4. Well, I claim now we have an equation. 1 to the 4/3 is 1. Cube rooted is 1. 1 times 6 is 1. So that's the equation. 6 plus c is equal to 4. So solve for c. Minus 6 minus 6. We then get that c is equal to -2. And so now I know specifically that my function f of x is actually 6x to the 4/3 minus 2. And so we found the specific function that we were looking for. And we're done. And an application problem. A flu epidemic hits a town. Let P of t be the number of persons sick with the flu at time t, where time is measured in days from the beginning of the epidemic and P of 0 is equal to 100. After t days, if the flu is spreading at a rate of P prime of t being 120t minus 3t squared people per day, let's find the formula for P of t. So what can we do? Well, first off, recognize that P of t is the same as the integral of P prime of t, because, if you will, integration and differentiation undo each other in such a way, because they're opposites from each other. And so the integral of 120t minus 3t squared dt, we always need that. What are we taking the integral with respect to? Well, what's that going to be? That's going to give us 120 t to the second over 2 minus 3 times t cubed divided by 3 plus some constant c. And clean that up a little bit. That is 60t squared minus t cubed plus that constant c. But then we're told that P of 0 is equal to 100. So let's plug in 0 for P here. That's going to be 60 times 0 squared minus 0 squared plus c. Excuse me, that's not squared, that should be a cubed. And so then this is c is equal to 100. So c is equal to 100, which means that my function P of t is specifically 60t squared minus t cubed plus c.